Hello everyone, you're welcome to my YouTube channel. I am Ridwan Ibrahim and I welcome you to the second part of the design. In the first part of the design, we have done the design of the base plates, and in this second part we will be doing the design of the anchor bolts. Alright, so basically what we have is a UC beam that is a vertical element. So we have a UC column, and every structural element needs to be supported on something. Okay, so this UC column is being supported on a concrete plate. So this is a connection between a steel and a concrete, and the connection that we are employing here is the anchor bolt and base plate design. So here there will be a base plate and then there will be anchor bolts. Okay, so the anchor bolt is that bolt that goes into the concrete. Okay, so it can be cast in place, it can be resin anchored, it can be mechanical anchor, it can be any type of anchor. All right, so it's just basically that element that goes into the concrete, and then it is the one that makes sure that the base plate is well seated on the concrete plate. So which simply means that when this bolt fails, the base plate is going to shift off the concrete plate. So when your base plate design is very correct and your anchor bolt design is wrong, then when the anchor bolt fails, the base plate automatically fails, even though the surface area and the thickness is well designed. Okay, so before we go into it fully, I will just explain the type of failure that we can have in bolts. Because when you are designing, basically when we say we are designing, we are just checking for the failures. We already know the type of failure that can happen in these structural elements. Then we want to check that, considering we have this type of load, can this element fail with these loads? Okay, so we have the three major load, which is the axial load, the shear force, and the moment. We have calculated that in the previous episodes. So we want to know if these loads are enough to fail the bolt. All right, so let's see what are the type of failure, or what are the mode of failure that we can have in anchor. The first one is the let's say tension or tensile failure. All right, tension or tensile failure, or you can just say pull out. Okay, pull out, so it can be called anyone. And then the second one is the shear. Okay, and then the third one is the bearing. Okay, so these are the three major type of failure that we can have in our boat. Okay, whether it is anchor or it is just a normal boat. Okay, so these three failure can then be elaborated depending on how elaborate your design is. You can say you have a single shear, you can say you have a block shear, or you have different kind of shear. All right, but these are the major three failures. All right, so let's treat the first one, which is the pull out. Okay, so what if you hear pull out, what does pull out means? So this is what pull out means. We have bolts here, right? Now let's assume that this bolt goes up. Automatically, if this bolt goes up, this one will come down, right? So if this bolt goes up, then we can say that is a pull out. So in that kind of case, you should be expecting to have something like this. You have your plinth, all right, and then your column will be something like this, right? Then your anchor will come up, right, while this one will go inside, because this has pulled up and then this will kind of come down. Okay, so you just need to imagine it. How can this bolt go up and this one come down? It is very easy. When you apply a moment here, okay, you apply a moment on this UC beam. Just imagine you are trying to rotate that UC beam. then you should expect this boat here to want to go up, and then this boat here to want to come down. So this boat is in tension, right? And then this boat will then be in compression. So when you have that kind of failure, then that is a pull out, because this boat at this position is already pulling out. So you can say pull out, or you say tension. So basically it is the moment that will cause pull out. And this is why we have calculated our moment in the previous episode, because we know the moment is what we call pull out in this case. So the second mode of failure is shear. So when will shear happen? Shear basically means when these bolts cut. Alright, so let's assume that you apply a force here, and then the position of this UC Coulomb changes from this position up to this position. Okay, so the black line represents the original position and the red line represents the new position. So now imagine that a force is being applied here to the original UC beam, and then the UC beam now moves to this position. What do you think will happen to this boat? Definitely the boat will cut. The top part of this boat we want to follow the column, whereas the bottom part has been cast in the concrete. So this will stay at the position, and then the top part of the boat will cut. So that is shear. So you can easily see that the shear force, which is the horizontal force, is the one that is capable of causing shear, whereas the moment is the one that is capable of causing the pullout. In this case, in some cases, the horizontal might also be causing pullouts, and depending on how complex it is, it might not be exactly like this. But in this kind of case, we can see that the moment is what we call pullout, and the horizontal force, which is the shear force, is the one that will cause shear. All right, and the third one is bearing. Bearing is more like shear. So, but when you look at it in the plan, it is just when you have your base plate like this, okay, and then you have the boat, you have the hole of the boat, and then you have the boat. So when you have this vertical force, when this vertical force pushes the UC column, then the boat here also tries to go in here, and then while it is trying to go in, it's cut across the plate. Okay, so if the hole that was in the plate before is 14 mm diameter, and the hole now widens up to look like maybe something like this, as this force is trying to push this UC beam, the boat is also going in that same direction as the force. Okay, so in that case, the boat has already sheared inside of the plate, so that is called bearing. Okay, so basically this is just going to cut across these three failures, which is the pull out, the shear, and the bearing. All right, so in the last episode we were able to make our analysis of the base plate. So the conclusion is that the length of the base plate is 300 mm wide, and the width of the base plate is 300 mm wide. Because this is a square base plate and then it is a column, I will say that the minimum number of bolts required is 4. Minimum. It can be more than 4, right? It can be 4, it can be 6, it can be 8, right? Whereas maybe you might want to try to pull one here, pull one here. You have your UC column. I'm just trying to draw the plan. So you have your UC column here. Maybe you can have one bolt here and one bolt here. If you have this is not advisable because of the lever arm. Okay, so I will say this is not right. Okay, so the minimum is meant to be 4. So sorry, I didn't want to clear that, but I'll just have to draw it one more time. So we have the plan. Okay, so we say we have one bolt here, we have one bolt here, we have one bolt here, and we have one bolt here. So this should be the minimum. If this does not pass, then you might consider introducing maybe one more here, one more here, or it could be one more here, one more here, depending on the direction of your forces, the direction of the force that is the most critical. Okay, so I will use this configuration, 4 numbers. So since our plate is 300 by 300 mm, I can assume that the spacing between this top bolt and this bottom bolt is 250 mm. After my design, if this is too small or if this is too big, we can then adjust it. But you know, it is just like a try and error method of design. You first of all assume, then if it works, fine. If it doesn't work, fine. In this other direction, which is side to side, I can make the same assumption that this is 250 mm. Okay, so let's just write out our known parameters. The known parameters. So the known parameters are just the parameters that we use in calculation, the ones that we know already. So the first one, I will say that we use 4 number bolts, right? So 4 number bolts, and then let the diameter be 12. So I will say M12, and then it is a single bolt. So it is a single bolt, and then it is ordinary bolts, and then it is grade 8.8 bolts. Okay, so M12, the 4 number that I mean here is basically the number, which is 1 2 3 4, and the M12, that is the diameter, which is 12 mm diameter bolt. And then single bolt simply means that it is a single bolt, because we have different kind of bolts. We have the single bolt, we have U bolts, we have N bolts, different shapes of bolts. So it's just a single bolt, which is normal, a bolt that is that looks like this, and okay, so that is the bolt. So, and then ordinary bolts, we basically have 2 types of bolts. We have the ordinary bolts and we have the HSFG bolts. Okay, so we are using the ordinary bolts, and then the grade is 8.8. There are different grades. There's 10.9, there's 4.6, and many more. So these are the known parameter. That's the first category. The second category is the spacing. So I can say that the bolt spacing is 250 mm as discussed. Okay, just as we discussed here. And then if this is 250 mm, if the spacing is 250 mm, then that will make the edge distance to be 25 mm. So what is edge distance? Edge distance is just what you can call pitch. They call it pitch sometimes. Okay, so that is the distance between the edge of your plate to the center of your bolt. Okay, so center of your bolt to the edge of your plate, that is it. So if from this center of the bolt to this center of the bolt is 250 and this whole length is 300, that means what will be remaining is 50. So 50 divided by 2 is 25, right? So I think that is clear why this is 25 mm. So the next thing will be the threaded area. Okay, number 4. So threaded area, the threaded area will be 84.3 millimeter squared. Okay, the threaded area is just a function of the diameter of the bolt. When you have a bolt like this and it goes like this, tread is just like that strip that you have in a boat. Okay, so the whole part of the boat is usually not treaded. So maybe this part here is the one that is threaded, okay, and this other top will not be threaded. So from this position up to this position, that is the length, right? That's the threaded length, and then this is the diameter of the boat. Okay, so it is actually a function of this, but you can easily find the threaded area. So now we are looking for the area. So you can check tables in your textbooks. The threaded area for a 12 mm boat is actually 84.3. For 16 mm boat is 157, and then many more like that. Okay, so that is the fourth parameter. The fifth parameter will be the ultimate tensile strength of the boat. The ultimate tensile strength of the boat is 800 Newton per millimeter squared. Okay, so you can check this in codes too, but this is not a problem. The ultimate tensile strength of boats is actually a function of the grade. Okay, so when you have grade like this 8.8, so if your grade is 8.8, this 8 actually stands for the ultimate tensile strength, which is this. So this 8 simply means 800. Why this 0.8 means the yield strength. Okay, so you just need to multiply 0.8 with 800. So 0.8 multiplied by 800, that will give you 640 Newton per millimeter squared. So this is the yield strength, and this is the ultimate tensile strength. All right, so if you have grade 6.4, what does that tell you? That tells you that the ultimate tensile strength is 600, and the yield strength is 0.4 times 600. I think that is clear. The sixth parameter is the thinner ply. The thinner ply is 10 mm. So what does thinner ply mean? Thinner ply simply means when you have a boat, let's say in this case, right, we have our UC beam and our UC column, and under our UC column we have the base plate, and then we now have our anchor bolt. You will see that the anchor bolt goes into the base plate, and the thickness of that base plate is 10 mm. Okay, so our thinner ply is 10 mm. Let's say in some cases you have UC column like this, and then under that UC column you have like a UC beam under. Okay, and then under that UC beam you now have your base plate, before you now have your plinth. Okay, so this is where your anchor bolt comes in. So in this case, you can see that your anchor bolt is going through two members. First of all, the flange thickness of this UC beam and the thickness of this base plate. So in order to know your thinner ply, it is actually the thinner of the two. So you have to confirm which one is thinner. Is it the flange of the UC beam here, or is it the thickness of your base plate? So whichever is the smallest, that is what you will record as your thinner ply. But in this case, we only have the UC column, and we have the base plates, and then we have the plinth, right? So our anchor bolt is going through the plinth alone. So since it is going through the plinth, we don't need to compare which other element is thinner in thickness. So it is just the base plate. So that would be the thickness of the base plate, and we have calculated the thickness of our base plate to be 10 mm in the previous analysis. Okay, so we go to the seventh parameter. The seventh parameter is the partial factor of safety. The partial factor of safety is just 1.25. So that is not something, that is like a constant. Okay, so number 8, that will be the grade of our base plate. Okay, I think we've done that earlier. The base plates grade, if I remember, we chose grade S275 and we said that the thickness is less than 40 mm, and that gave us the design strength of 265, right? So in this case, the reason why we need the base plate grade is also to know the strength, right? But in this case, the bearing strength, okay, not the design strength, the bearing stress, okay, because I explained to you that the bearing, when we say bearing, the plate is the actual member that goes through bearing, although there is both bearing and plate bearing, but the plate bearing is the more critical one. So since we know the base plate grade, then we can know the bearing grade. So you can check your textbooks, or you check just check the tables in your code. So for S275 grade, the bearing strength 460 Newton per mm squared. So for grade 235, for grade 355, and other grades, they have their bearing strength too. So you just need to check textbooks for that. This is not a figure you need to put in your head. So what about our forces? We have done the calculation of our forces. What is our axial force? 83.04 kilonewton. Our shear force is 11.34 kilonewton, and our moment is 16.625 kilonewton meter. So I think this will be all. So if this is all of our known parameters, then we just need to check our steel. So I've explained earlier that what we are checking is 3 failures. We are checking it against pullouts, we are checking it against shear, and we are checking it against bearing. Okay, so let me calculate. Let me say forces. You might be wondering, what force am I talking about? Because we've already calculated these forces, and that's what I've written out, right? So yeah, that's very correct. However, this is the force from the Coulomb. We want to talk about the force on each bolt. So if you have 4 bolts, if let's say for example now the axial force from the Coulomb is 83.04, and then we have 4 bolts, are you saying 83.04 is the force on each bolt? No. So we just want to know what is the force on each bolt, the axial force on each bolt, the shear force on each bolt, and so that is what we want to calculate now. So let's start from the shear. Number 1, or let me say A, shear. As I've explained, shear is I think I've cleared that. Okay, yeah, here, as I've explained, shear is when you have your force going in this way, and then it cuts across your bolt, then your bolt cuts. Okay, so, or your bolt breaks. That is what we call shear, right? So you can imagine that you have a Coulomb like this, and then you have an horizontal force that is trying to push the Coulomb. You will see that the force will push away the 4 bolts as well. Is that right? So we can say that the 4 bolts are going to experience shear together. So in that case, the shear force is just going to be the total shear force divided by 4. So our total shear force is 11.34, and when shear wants to happen, it's going to happen on the 4 bolts. So I just need to divide that by 4, and that will give me 2.85 kilonewton. So that means the shear on each bolt is 2.85 kilonewton. That is the shear force on each bolt. So I just need to know if the shear capacity of each bolt is not less than 2.85. Because if the shear capacity of the bolts of each bolt is less than 2.85, that means this shear force is strong enough to shear the bolts. But if the shear capacity of the bolt is greater than this calculated shear force, then the bolt will not shear. All right, so we've known the shear force on each bolt. Now let's know the pullouts on each bolt. So as explained earlier, what pullout means is when this bolt is going up, right, something pushes it up. If this bolt pushes up, that means this one will come down. All right, and I told you that that is when you apply a moment. So you can just imagine you try to twist this column. So this side we try to go up and this side we try to come down. So if we have 4 bolts and then you apply a moment in this direction, right? So that means these bolts will pull out, these bolts will pull out, whereas these bolts will come in, and then these bolts will come in. So these 2 bolts will be in tension while these 2 bolts will be in compression. So you can easily say that whenever you want to have pull out, it is 2 bolts that are working, okay? And when we want to have shear, it is the 4 bolts that are working, okay? Because if I want to have pull out here, 2 bolts we pull out while 2 bolts we push in, okay? When the bolt pushes in, it is not a failure because definitely we push the bolt in before, but when it pushes out, then that is a failure, right? So as we have explained, it is the moment that will cause the pull out, right? So so you can say that the pull out is just the moment over the lever arm times the number of bolts that will pull out, because we are trying to resolve this into force. So if moment equals to force times distance, okay, definitely force will be moment over distance. So that is why you have this moment over the distance, which is the lever arm. And which lever arm am I talking here? Am I talking about, I said if we have a bolt, I said if we have a moment applied in this direction, then this bolt will pull out, so this bolt will pull out, this bolt will push in, this bolt will push in. So you can see that the lever arm is just between these bolts that are pushing in and these bolts that are pushing out, so which is this distance from here to here, and that has been computed to be what, 250 mm. So this one, all right, 250 mm, that's the thickness. So what is our moment? Our moment is 16.625 divided by the lever arm of the pull out, that is 0.25, that's 250 mm. And how many bolts are pulling out? Just 2. So divide by 2 times 2. So our pull out force will now be 33.25 kilonewton. I think that is clear. Another thing you might want to consider is the compression. Although compression is not a problem, because when we have a force that is compressing our boat downward, that is like a good thing, that is like what we want, okay? But when it is pushing out, that is a failure. When it shears, that's a failure. So what I'm trying to point out is that when you have a vertical pole like this, and then we have our boat inside, the axial force of this boat will be pushing this boat inside. Is that not so? So if the axial force coming from this UC column is pushing our boat downward, is causing compression on this our boat, that means I can subtract that compression force from this tensile force that we have calculated. I don't know if that is clear. So if the compression force, what is the axial force from the column? The axial force is 83.04, and then that force will be compressing the 4 bolts downward. So if you look at it from the plan, we are just saying that okay, the bolt or the load from this bolt, it will be compressing down this base plate and compressing down the 4 bolts together. So these 4 bolts will be in compression altogether. So we can say this force divided by 4, that will be 20.76 kilonewton. So in this case, you can say that your total pullouts per boat should be 33.25 minus 20.76, because as this force is trying to pull out your boat, this force is trying to push down your boat. So depending on which one is now greater, that will for example, if the force pushing it down is greater than the force pushing it up, that means pull out will not occur. But if the force pushing it down is less than the force pushing it up, that means pull out will occur. So we can say that from here the total pull out will be 12.49 kilonewton. However, for conservativeness, I can pretend as if this is my pull out force, as if this compression is not happening, because as an engineer you want to design for the worst case. This compression is a force in your favor. So because this force is in your favor, you might decide not to include it in your calculation so that you can have the worst case. So if this 33 kilonewton passes, then it is fine. But if this 33 kilonewton does not pass, then you might try to come and include this in your calculation in order not to have over a large margin for your design. Okay, so since all of the forces that are going to cause failure has been established, this is the force that is going to cause shear on our bolts. It is the same force that will cause bearing on our bolts. Okay, this is the force, this one is the force that will cause pull out on our bolt. Okay, similar to this one, but I said let's go with this one and pretend as if this one will not, because this force here is as a result of including the compression force. So if I ignore the compression force, let me just go with this one. Okay, because this one is bigger. So if this passes, then I am more at the safer side. Okay, so this that we have calculated is actually the forces that is going to cause shear and pull out. So now I want to calculate the capacity. I want to know what my shear capacity is. I want to know what my tensile capacity is. So let me calculate the capacity. So let me say capacities. I'll change the ink to black. So number one, I will calculate my tensile capacity. The formula for tensile capacity is 0.9 multiplied by FUB multiplied by A threaded multiplied by the partial factor of safety. Alright, so if you put this is 0.9 multiplied by FUB, that is your ultimate tensile strength. So that is it here. The ultimate tensile strength is 800. So you multiply this by 800 multiplied by your threaded area. For 12 mm threaded area is 84.3. okay, the threaded area is 84.3 millimeter squared. So this is 84.3 millimeter square, and your gamma M12, which is your partial factor of safety, that is 1.25 as discussed. So if you put all this, you will have 90.43 kilonewton. So this is your shear capacity. Sorry, this is your tensile capacity. So what does tensile capacity mean? Tensile capacity is just like the capacity of that bolt in tension. So this is our tensile capacity. So you check your tensile force. What is your tensile force? Your tensile force is 33. So since 33 is less than 90.43, then you can say that your anchor is okay in tension or okay in pullouts, because the tensile capacity is greater than the tension force. So we have confirmed one of the three failures. So we'll go to the second failure, which is the shear. So now let's calculate our shear capacity. The shear capacity, the formula is almost the same. So that is 0.6 multiplied by FUB multiplied by your threaded area divided by gamma M12. So the only difference is that this one is 0.9 and this one is 0.6. okay, so if you put this in the formula, you should have 60.3 kilonewton. So this is our shear capacity. shear capacity. Okay, this is your shear capacity. So now you compare your shear force to your shear capacity. So what's our shear force? Our shear force is 2.85. So 2.85 is very low compared to 60.3. So you can also say that your anchor is okay in shear. Okay, so the third one, so now we have to calculate the bearing capacity. So the formula is FUB multiplied by DB multiplied by TP over your gamma Y12 as usual. So what's FUB? That's the bearing capacity of your plates, and we said that for S275 grade of plates, the bearing strength, which is the bearing capacity, is 460 Newton per millimeter. And what is dB? dB is the diameter of your bolt, which is 12, and then TP, that is the thickness of your plates, which we also call the thinner ply, right? Thinner ply. So that is 10, and then what is this? This one is 1.25, and we expect that to give you 44.16 kilonewton. Okay, if this is your bearing strength, you need to compare your bearing strength with the shear force. It is that same shear force that is capable of making the bolts to shear. It's the same force that is capable of making the plate to undergo bearing. So you have to confirm that, you have to compare that with your shear force. So your shear force is 2.85 and your bearing capacity is 44.16. So this anchor and the plates, anchor and plate, is okay in bearing. Okay, so these three major force has been calculated. So we have done the major part of the calculation, which is the capacity. So we've confirmed that the shear capacity is okay, the tensile capacity is okay, and the bearing capacity is okay. So that is the first part of the design. The second part of the design is that you need to confirm if the edge distance that we have used, the edge distance we have used is 25 mm and the spacing that we have used is 250 mm. You need to confirm if these are adequate. You might be wondering why that is necessary. Definitely it is necessary. Let's assume that you have, in this case our edge distance is 25 mm, right? If you have a plate like this and you have your hole and your bolt very close to the plate, so if the edge distance is very small, now imagine that you want to have a bearing failure. The bearing failure will happen very fast. Here you just see that this will look like this. This will look like this. The hole here will just cut across the plate easily, simply because the edge distance, which is the distance from the center of this bolt to the end of this place, is very small. So when you have a small edge distance, bearing is liable to happen very fast. Okay, but when you have adequate edge distance, then you can beat that. The second one is the pitch, which is the spacing between the bolts. The spacing between the bolts is also a parameter, because don't forget that when you are trying to calculate your pullout, the spacing is essential. So if the spacing is too small, then you'll be expecting your pullout force to be very high. Okay, because from here you can see that the relationship between your pullout force and your spacing is actually inverse. So when this is small, this will be big. So if you have a very small pullout, when you have a very small spacing between the bolts, then you should be expecting your pullout force to be very big. And when your pullout force is very big, then it might be greater than your capacity. so that can make your boat to fail. So that tells you how important the spacing between the boats is. Okay, so you need to confirm if this if this spacing is adequate or not. You also need to confirm if the edge distance is also adequate. Okay, so I will just rush into that. So apart from checking for the capacity, you also need to check for all these spacings. Okay, the minimum boat spacing. The formula for the minimum boat spacing is actually the lesser value between 2.2 dH and 2.5 dB. So what is dH? dH is diameter of hole, dB is the diameter of boat. So what's dH? 2.2 times diameter of hole is 14. So if my boat is 12 mm, I expect my hole to be like this. So 1 mm to this side, 1 mm to this side, because there needs to be a tolerance for the boat to go inside the hole. So that is 2 mm, 1 meter to 1 mm to this side, 1 mm to this side. Okay, so diameter of hole is this, and then this one 2.5. diameter of boat is 12, right? That will be 30.8. that will be 30. Okay, so that is almost the same. So you now pick the lesser is 30. So now you need to go and confirm that the minimum spacing between your boat must not be lesser than 30. So if you confirm our own, what we have used is 250 mm, right? The spacing between our boat is 250 mm, so that is very well greater than 30. Now we will go to the minimum edge distance. The edge distance that we have used is 25, right? So we want to know if it is lesser than what is minimum or if it is okay. So what is our minimum edge distance? The formula for minimum edge distance is 1.2 dH, which is diameter of O. So 1.2 multiplied by diameter of O, which is 14, right? 16.8 millimeter. So you see that 16.8 millimeter is actually lesser than 25. Okay, so we have used a edge distance that is greater than the minimum. You cannot use anything less than the minimum, but you can use more than the minimum, definitely. So if you use anything lesser than 16.8, then you should be expecting to have a bearing failure. Okay, so it's not just about checking your bearing capacity against your bearing against your shear force. You also need to check your edge distance. Okay, so because the edge distance will aid the bearing. So that will be all for anchor design. We have checked for the capacity and we have also checked for the spacing and edge distance. So this will be all for this course. See you next time, and thank you for watching.